Hello students, after having spoken about electric field in my previous video, now I will talk about electrostatic potential, which is also the second major topic in electricity. So electric potential difference between the 2 points in an electric field, it will be defined as the work done in moving a unit positive charge from one point to another against the electrostatic force. Whatever is written, I can see here, if you see, there is a plus charge Q which is placed at a point P, and there is a charge plus Q naught. I am moving a charge Q naught from point A to point B and trying to bring it near to this. As you know from the Coulomb's law, since these are two positive charges, there will definitely be a repulsive force which will act against the movement of the plus charge Q. We are moving it from A to B, we are bringing it nearer to plus charge Q, whereas the force is acting away from it. So positive work done, positive work done is done by the system. So the potential at point B will definitely be higher than A. Okay, so work has to be done against the force to bring it from point A to B. So it is given by VB minus VA is equal to work done between A and B divided by Q naught. So this is work done in moving a touch charge from A to B. I have clearly written at this place. If the point A lies at the infinity, if I take point A at infinity, then what will happen? There will be no influence of electric field because of plus charge Q. Because only when the electric field exists, there will be a force and the point will move from A to B against a force. Now if one point is at infinity, we assume that at infinity the electric field diminishes. So if there is no electric field, so potential at that point at infinity will be 0. So if I put VA is equal to 0, so potential at any point V is given by WAB divided by Q naught. So this is nothing but W upon Q naught. So electric potential at a point in an electric field. So I will write here electric, this is wrongly written, electric potential. Electric potential at a point in an electric field is defined as the amount of work done in moving a unit positive charge from infinity to that point against the electrostatic force. So we are bringing a unit charge from infinity to that point, and whatever work is done in bringing it from infinity to that point by a unit charge is given by the is called as electrostatic potential at that particular point. So electric potential is nothing but work done divided by charge. Now electric potential due to a point charge. Now here again I am drawing the same type of figure. There is a plus charge Q and at a distance R there is a point P. So in this we will try to find out what is the electric potential at a point P. So we will go by the same theory and the basic fundamental of the electric potential with what we have explained above. In this figure, a charge Q naught is brought. I am bringing a charge Q naught from infinity to point P. So work done in moving a small charge, in moving a small distance dx. If I am moving a charge Q naught to a small distance dx from A to B, I am moving in this direction, A to B. So here I have drawn dx is in this direction, force is acting in this direction. There is an angle of 180 degrees. They are out of phase. So dx is in the negative x direction where force is acting in the positive x direction. As the displacement is against the force, so the work done will be given by dw is f dot dx. Dot means it's a dot product. Dot product means work done. Then is dw is called a dw is a work done. So it will be a scalar quantity. It will not have any direction. So I can write it as f dx cos 180 degree. So we will talk about this in more detail about dot product and cross product when we will cover the chapter of vector products. So dw is given by minus f dx because cos 180 degree is minus 1. So force you already know from the Coulomb's law. F is equal to 1 upon 4 pi epsilon naught q naught by x square. If x is the distance between the charge q and at a point B, which is at a distance x. So it is q naught by x square. Now, so the total work done in moving from infinity to distance r, I am bringing it from infinity to a distance r at a point p. When I am bringing it from point b, so I will just add up all the small work done from infinity to r by doing an integration. So substituting the value of f here and dx, you can see that all the constant quantities have come out and it is 1 upon x square times of dx. So by applying the formula of integration, so 1 upon x square, that integral is minus 1 by x, and when the value is substituted, w is 1 upon 4 pi epsilon naught q naught by r. So this is also the potential energy. You can see if a charge is brought up to, instead of going and explaining about the potential energy later on, I will explain it. If the charge is brought up to a point p at a distance r, if from infinity to that point, now the charge comes here, q naught has come here, an explanation. So when it has come to this point, what happens? The work done will be 1 upon 4 pi epsilon naught q naught by r. So you must remember, if there are two charges which are placed at a distance, positive charges q naught at a distance r, so the work done or the potential energy stored between them will be given by 1 upon 4 pi epsilon naught q naught by r. Now the work done per unit charge, I will divide it by q naught. So this will give 1 upon 4 pi epsilon naught q by r. So this is the formula, that work V potential at a point P, distance r from the positive charge plus q, is given by 1 upon 4 pi epsilon naught q by r. Now the important point which must note about the electric potential is that it's a scalar quantity, because we have done the scalar product of work done and then we have divided it by unit charge. So potential is a scalar quantity, whereas electric field is a vector quantity. So I have explained about the net electric field because of the system of discrete charges at a point P, where we had taken the vector sum of electric field of various charges at that point. Now here I am taking a electric potential due to the system of charges. So if there are Q1, Q2, Q3 charges which are placed at a distance R1, R2 and R3 from a point P, so what is the potential P? So it is nothing, since it's a scalar quantity. So potential at a particular point will be nothing but the vector sum of the potential due to individual charges at point P. So I have just added Q1 by R1, 1 upon 4 pi epsilon naught Q1 by R1, 1 upon 4 pi epsilon naught Q2 by R2 plus 1 upon 4 pi epsilon naught Q2 by R3. So I have taken 1 upon 4 pi epsilon naught as common. So this is nothing but the algebraic sum. This is quite simple with respect to the electric field, where the electric field is a vector quantity and we have to do the vector sum instead of doing the algebraic sum. You must note this point because these kind of questions come in the examination. Now I will quickly come to a very important point. What is the relation between electric field and potential? The same theory, the same method I have adopted here. Now there is a plus charge Q and there is a point B which is at a distance R. So I am bringing a charge Q naught from A to B. So I am moving it at distance dr. You can see dr towards the plus charge Q. You know that charge is plus Q, so electric field will be acting away from the charge. So here its direction will be opposite to the displacement. It is opposite to the displacement, which I have drawn here. So work done will be nothing but FDR, and I have already explained, and you know that F is equal to Q naught into E, which is already explained by me in my video on electric field. So F is equal to Q naught E, so that value I will substitute here. So dW will be nothing but Q minus Q naught E into dr, because cos 80 degrees, cos 180 degrees minus 1. So dW is minus FDR. So making use of that, dW will be minus Q naught E into dr. But at the same time, I have explained about the electric potential also. Electric potential is nothing but the work done by the unit positive charge unit positive charge in bringing it from infinity to that point. So for the small work done, dV is given by dW by Q naught. So same thing, dW value I have substituted here as Q naught into dV, and here Q naught into E into dr. So equating equation, I am equating equation 1 and 2. So Q naught gets cancelled. So E is equal to minus dV by dr. This is one of the very important relation you must remember, because this relation will help us to solve many of the problems related to continuity, continuous charges, and in the capacitance where the electric field is variable. Hmm? So we will come to those applications and examples while we follow more of our videos on this. So you must remember at this point that the negative sign, what does this negative sign shows? It shows that electric field is in the direction of decreasing potential. You can see here, electric field, direction of electric field is in the direction of decreasing potential. Potential is decreasing from VB to VA. So the minus sign is a significance, has a significance in the sense that we can say electric field direction is in the direction of decreasing potential. This is very important and you must remember. Now I can integrate this and by integrating this I will get another result. If one point is at infinity, so I will integrate between point A and B, which is R1 and R2, which is at a distance R1 and R2. So integration is done. If R1 is at infinity, VA will be 0 as explained earlier. So your potential will be defined as minus infinity to R E d R. So this is very important relation. We'll come with the numerical examples and the capacitance, and we'll and relation and many other applications and solved examples on this in our coming lectures.